So we'll continue with resting membrane potential and action potentials within a muscle fiber. I'm going to also mention that that the same thing happens within the walls of a neuron. And so everything that we're going to say here also works in nerves. Now, before I get started, I want to talk about facilitated diffusion and channels that facilitate the diffusion. Facilitated diffusion is a passive process. All that has to happen is there has to be a concentration gradient. There has to be more of a substance on one side than on the other. And diffusion will happen if there is a channel that facilitates that diffusion. In the plasma membranes of cells, there can be 4 different types of channels. The first one is something called a leakage channel, a leak channel. And this is a channel that's always open. So if the sodium potassium pump is pumping using ATP, active transport, pumping sodium out of the cell and potassium into the cell. It pumps 3 sodiums out and 2 potassiums in. What will happen will be that there will be a concentration gradient created by that active transport. There will be more sodium outside the cell than inside the cell because we're actively pumping it out. Sodium will want to diffuse back into the cell if it can. If there's a channel that allows the passage of sodium and that channel is open, sodium will diffuse into the cell by facilitated diffusion. If the channel is a leak channel, it is always open. So sodium gets pumped out and it leaks back in. Then gets pumped out again and leaks back in. And gets pumped out again and leaks back in. Potassium gets pumped in and leaks out, etc. Calcium, if it was a calcium channel, pumped out, leak back in, that kind of thing. There's another kind of channel called a ligand-gated channel or a chemically gated channel. And this is the channel is closed unless there is a chemical that has adhered to the channel, a ligand, a hormone or a neurotransmitter, that causes that channel to be open. That in the presence of the neurotransmitter acetylcholine, the sodium channels in the synaptic cleft, the sodium channels in the motor end plate, will be open. Without acetylcholine, they are closed. When they are open, sodium can leak into the cell. When they are closed, sodium can't leak into the cell. A third type of channel is something called an electrically gated channel. And so these are closed at rest, but open when there is an electromagnetic field happening. So they are closed when there's positive charge outside and negative charge inside the cell. When the inside of the cell becomes more positive or the outside of the cell becomes less positive, the channel opens. Now, sodium is a positive ion. So we pump sodium out. We not only have more sodium outside the cell, but we have more positive charge outside the cell. The cell is called polarized at this state because outside is positive compared to inside. That is polarized. If we let sodium come into the cell depolarizes. It becomes less different. When it's less different, the electrically gated channels open to allow even more sodium to come in and further depolarize. The fourth type of channel, which we will not talk about in this discussion, but will come later in the course, is something called a mechanically gated channel. And these are channels that open up in response to a physical deformation of the cell membrane, that pressure causes them to open. So no pressure, no sodium, channels open, pressure, sodium channels open, and depolarization happens. This is how the sense of touch works. But for skeletal muscle, it doesn't come into play. As a matter of fact, the only thing that comes into play with skeletal muscle are the ligand chemically gated channels and the voltage gated channels. There are some leak channels, especially for potassium, uh, but the two main ones are chemically gated and voltage gated. Okay, because of the sodium potassium pump, sodium is pumped out of the cell. Positive charge. Potassium is pumped into the cell, also a positive charge, but 3 sodiums get pumped out to every 2 sodiums that come back in. Potassium can actually leak through the leak channels, but it is got 2 competing forces. There is the concentration gradient of potassium that wants potassium to leave the cell, but it is counterbalanced by the electrically gradient of the positive charged potassium doesn't want to go towards the more positively charged outside of the cell, the sodium. So the equilibrium is found between those two forces, the chemical gradient and the electrical gradient. So normally there's not much exchange of potassium. So this is called the resting membrane potential. It is potential energy here. I'll come back to this. I'd actually like to go to here. I'm sharing a bit of the whiteboard from, I want to do something on the whiteboard here. Okay. This is a membrane. It's a fence. And for the sake of analogy, let's say on this side of the fence is a boys' school, and on this side of the fence is an all-girls school. And I'm not meaning to be anything about this, just okay. On this side of the fence, there's a whole bunch of boys. Where are you going to find them during recess or during when there's no classes? The boys are all going to be hanging out close to the fence. And the girls are going to be hanging out close to the fence, right? Because there's an attraction. The is there a problem here? No. Is there a potential problem? Yes. This is a representation of potential energy that the that because of the attraction that are held separate by the fence, there is boys hanging out this way, girls hanging out that way. Okay? So if a gate opens in the fence right here, and it allows the boys to come in, what's going to happen? Well, this boy is going to come to this side. Right now, the fence is polarized. When the boy comes across, it is now depolarized. So now this side is less different than it used to be. Okay. When he comes across, the first thing the little bastard does is he opens the next gate and allows this boy to come across. So now this spot is depolarized. And when he comes across, the first thing he does is he opens a gate right here that allows this one to cross. And that depolarizes right here. He opens the next gate, and then this guy comes across. Okay? Depolarizing right here. But in the meantime, the teachers on yard duty get wind of what's coming, and they throw this bastard back over here, and they close the gate. And then this one comes across here, and the teacher throws this guy back, closes the gate. And then this depolarized opens the next gate, and this one comes across. And the teacher throws this one back, repolarizing, and closes the gate. And so on. And so on. Okay, and so what we're going to get is this little wave of depolarization moving along the length of the fence, with boys coming across, depolarizing the fence, and teachers following behind, repolarizing. Just making sense? And it will move along like a wave, just like the wave at a Blue Jays game where people stand up one after another. That the nothing runs along the wave, it's just people standing in their seats and sitting back down. It's going to be the same here. Sodium will cross because the gate is open by both its concentration gradient and the electrical gradient. So it's going to happen very quickly. There's more sodium out here than inside. There is more, well, I'm sorry. The boys will come across because of the concentration gradient, more boys over here than over here, and the attraction. Okay, but we're going to have this wave of depolarization moving along. Depolarize, repolarize, depolarize, repolarize. Make sense? So just substitute sodium and potassium, but we'll stick with sodium right now. uh, for boys and girls. So these are the electrically gated channels, these gates, along the entire length of the membrane. Sodium is outside because the sodium potassium pumps it outside. A gate gets opened up. Sodium gets to come through that gate. So that means that the place where the gate opens up, the very first gate opens up, depolarizes. That depolarization opens the electrically gated channel right next to it, which then allows sodium to come in to depolarize that spot, which opens up the next electrically gated channel and the next electrically, and we will have this wave that will move right along the entire length of the membrane, a wave of depolarization, right? The gates close almost immediately and it repolarizes. Cool? Okay. There are leakage channels to sodium or to potassium here. So what's going to actually happen is this. When the sodium comes in, which is the black line, now the inside becomes more positive. The potassium that's in here will now want to go out the leakage channel because of its chemical gradient, the fact that there's more potassium in than out. But now it was being resisted by the positive charges out here. Now it's not being resisted by the positive charge out there because the positive charge is now in here. As a matter of fact, it's going to repel the potassium. So potassium is going to be the one that leaves. But when potassium leaves, it's taking its positive charge with it, which is going to make the outside positive again and make the inside less positive because the potassium's leaving. So actually, it's not that sodium gets pushed back out, but potassium gets pushed back out in each one of these cases. And when potassium gets pushed back out, it repolarizes the membrane. The outside becomes more positive again, and the inside becomes less positive again. So now it's repolarized, which then closes the electrically gated sodium channels. Okay, so now we have this time frame when there's all kinds of potassium out here and all kinds of sodium inside. And then the sodium potassium pumps the sodium out and the potassium in and resets the resting membrane potential. Okay, so the membrane, we will do this. The membrane, remember, has got these invaginations, the T tubules. And this negative charge continues down here, and the positive charges continue down here. But there's also this. the sarcoplasmic reticulum. Okay. And the sarcoplasmic reticulum is full of calcium. So the inside of the sarcoplasmic reticulum is full of calcium. So out here, we have, come on, there's not enough room there. Out here, we have negative charges. Okay. And in here, we have all of these positive charges. So when the sodium, when this wave of depolarization, which is called the action potential, reaches here, it goes down the T tubule, and now sodium comes in and depolarizes this space. So now there is a polarization of this membrane, but there's also a polarization of this membrane between this negative charge and this positive charge. When the sodium comes in, now inside is positive, which means that the sarcoplasmic reticulum is now depolarized, and electrically gated calcium channels open, and calcium leaves. When this repolarizes, because the potassium gets chased out, so we get a repolarization, then the calcium gates close here, and the sodium gates close here. And we've repolarized. We use the sodium-potassium pump to reset the sodium and potassium levels here. And then we pump, because these gates are closed, now the calcium gets pumped back in by active transport of the calcium pumps. So when the sarcoplasmic reticulum is depolarized, calcium is released out into the sarcoplasm. And when the sarcoplasmic reticulum is polarized, calcium gets pumped back in. So what that means is that if we go all the way over to here, and I have a gate here that is a chemically gated channel, and acetylcholine binds onto this gate. It opens a sodium channel, which allows sodium to come in here, depolarize this area, which pushes the potassium out. But this depolarization opens the adjacent electrically gated channels and starts this action potential. So a molecule of acetylcholine opens a ligand-gated channel, depolarizes part of the motor end plate, which causes the electrical gated channels to start opening sequentially and an action potential, and then repolarization by potassium being chased out. The action potential moves along the membrane, down the T tubule, which depolarizes the space between the sarcoplasmic reticulum and the T tubule, which then depolarizes the sarcoplasmic reticulum, which releases calcium. Oh, sorry. Which releases calcium, Ca plus plus, out into the sarcoplasm. And then when this all resets, the calcium gets brought back in. So a little bit of acetylcholine in the synaptic cleft causes this chain reaction to happen, and calcium is released into the sarcoplasm. Okay, so this is a much more anatomically accurate view of this. Action potential comes down the axon, allows calcium to enter the synaptic knob, which causes the vesicles of acetylcholine to release into the synaptic cleft, which cause the ligand-gated sodium channels to open. Sodium diffuses into the cell, depolarizing the motor end plate, which causes the electrically gated channels to open, allowing sodium to come in and depolarize. A wave of action potential moves along the T tubule, which causes depolarization of the sarcoplasmic reticulum, which releases calcium out into the sarcoplasm, which binds to the troponin. If you remember, the troponin molecule on the thin filaments has a calcium receptor. And this will happen along every T tubule, surrounding every myofibril, at every sarcomere, in the entire muscle fiber, more or less simultaneously. We're going to see that the calcium causes an interaction between the thin and thick filaments that causes contraction. So the trigger of acetylcholine causes the action potential, which causes the release of calcium, which causes the contraction, and the sarcomere shortens. So nerve signal travels down the axon, voltage-gated calcium channels open, calcium goes in, binds to the surface of the vesicles, it releases acetylcholine into the synaptic cleft. Acetylcholine molecules are released, and it binds at the end plate, causing excitation of the skeletal muscle. It causes the action potential to start and propagate along the sarcolemma down the T tubules, which then causes the depolarization of the sarcoplasmic reticulum, which causes the release of calcium from the sarcoplasmic reticulum into the sarcoplasm. Right? So again, acetylcholine receptors are chemically gated channels. Sodium diffuses into the cell, which pushes potassium out. So briefly, the cell membrane becomes less negative, right? And causes the action potential to happen. Sodium comes in very quickly through the voltage-gated channels, and the chain reaction occurs. Right? So right after the sodium channels open, they close, and potassium starts to diffuse out of the cell. And that's aided by voltage-gated potassium channels. The things that open the sodium channels also open potassium channels and facilitate that diffusion much more than the leakage. So there's a quick repolarization. So at this point, the cell membrane is polarized again because potassium's on the outside and sodium's on the inside. The outside has returned to a positive nature, but it's the wrong ions outside versus inside. And we have to reset the right balance of ions using ATP and the sodium potassium pump, and that takes time. If there's sodium outside, you open another ligand chemically gated sodium channel at the motor end plate, nothing's going to happen because there is no concentration gradient yet. So we call this the refractory period. This is the time when the muscle cannot respond to another signal. We have to reset the membrane resting potential, putting sodium outside and potassium inside in order to allow this to happen again. So this is the channels opening, sodium coming in, potassium going out. The potassium channels are these blue ones. The voltage-gated sodium channels are these purple ones, lilac-colored ones, and they kind of work together to propagate a wave of depolarization called an action potential. So there's a trigger level. It's called the threshold. We have polarization to about 90 millivolts. We have to have depolarization to reach the threshold to cause the electrically gated channels to open and have massive depolarization. And then we have the repolarization happens that brings it back down to below threshold. And then we have the sodium potassium pump resetting the resting potential here. Right? So this is repolarized. However, it's repolarized with the wrong, it's repolarized with the potassium, not the sodium. So this time here is the refractory period. Again, the action potential goes down the T tubules, causes the calcium channels to open the calcium channels of the sarcoplasmic reticulum. Calcium is released, and calcium interacts with the myofilaments, and it triggers contraction. Okay, I'd like to stop right here, and we'll do the next video on how the calcium interacts with the thin filament and how the contraction happens.